People in the back hear me? Can people in the back hear me? Okay. Is it better? Oh, no. Okay. How about now? Is it better? Okay, I will try to do my best. Okay, hi everyone. My name is Zhenbang Dai. I'm a postdoc here at UT Austin with Professor Feliciano Giustino. So I'm gonna show you another example of what we can achieve by letting EPW and Berkeley GW talking to each other. That is, we can compute the exciton polarons from first principles. So I will spend most of my time in this talk discussing the theory of the excitonic polarons. And then I will, after showing you the theory, I will give you a brief preview of the workflow that with EPW and the Berkeley GW. Because this feature is not really released yet, so I will only touch upon the what you can expect when the feature is released, and then I will show you a few examples about the calculations in real materials. Okay, so I think Feliciano yesterday gave us a very nice lecture about polarons. So today I don't need to tell you the importance and the application or the theory of the polarons in detail, but just a very quick reminder. A polaron is a quasi-particle that is formed by an extra charge, such as an electron in this case, and the induced local lattice distortion. And similarly, in the case of excitons, which is a neutral particle, it can also have a similar polaronic physics. So you might wonder, like, exciton is a neutral particle, so why would this neutral particle interact with the local ions? Well, the reality is that if you have done some BSE calculations, say using Berkeley GW, then often the case is that the electron density and the hole density in the exciton are not overlapping with each other exactly. So because of this local charge fluctuation, it can still generate some electric field, and this electric field might interact with the ions surrounding the exciton. And because of this interaction, there's a possibility that the excitons can be further stabilized by the lattice distortion induced by this interaction. And we call this quasi-particle excitonic polarons or self-trapped excitons sometimes. And you might wonder why this exciton polaron is so important and why we're interested in it. Well, it's because excitons are very important in optics. It determines a lot of optical properties in the real materials. And because of this extra interaction between the exciton and the phonons, the properties of excitons can be further affected by these exciton polarons. For example, here is a plot where it shows the absorption spectrum and also the photoluminescence spectrum for this very novel double perovskite that Feliciano discussed briefly yesterday. So basically, if there is no formation of the exciton polaron, you would expect that the absorption on-site and the photoluminescence peak will coincide with each other because they should have the same energy. But in reality, what people found in experiments that there is a big shift between the absorption on-site, that is denoted by the solid line, and the photoluminescence peak, which is denoted by the dashed line. And this shift is sometimes called the Stokes shift. And people attribute the formation of the exciton polaron to this large Stokes shift. So it will be preferred if we can have some ab initio theory that can allow us to calculate or even predict the exciton polarons from first principles. Okay, we are definitely not the first one to have this idea, and people have done theoretical calculations before by using different methods. For example, in this, there are basically three categories that allow people to do this calculation. One of them being some high-level quantum chemistry methods, meaning you can use a lot of Slater determinants to expand your wave function, Mandelbrot wave function, and you can get your total energies for the excited state and the force in a very accurate way. But as you can imagine, this method can be very expensive. So it's not very appropriate to deal with large systems with hosting large exciton polarons. The second method is still in the theory of DFT. So basically, you're still using a single particle theory, but instead of only caring about the ground state charge density, this time in the self-consistent iteration in the DFT calculation, you impose the occupation of the conduction band minimum, and you will generate a new charge density corresponding to this excited state, and then you finish your self-consistent iteration. And yeah, you can get some results of some quantities from this scheme, but as you know, DFT is an effective single particle theory, so it cannot really capture the complicated electron-hole correlation. So we don't know, to what extent we can connect the calculation here to experiments. And there's the third method that was done by Professor Louis and his former postdoc, Ismail Beji, where they have a very interesting theory by computing the excited state force. And the force is basically a first order derivative of the excited state total energy with respect to the atomic displacement. And in their theory, the excited state total energy is composed of two parts. One is the ground state energy, which you can accurately calculate it from DFT. And the second part is the excitation energy. From the talk by Professor Liu yesterday and also the talk by Professor Zhengbu Li just now, we know that we can use BSE or Bethe-Salpeter equation to get the excitation energy very accurately. And they use this method to successfully capture the self-trapped exciton or the exciton polarons in the alpha quartz. So as you can see later, our methods receive a lot of inspirations from this method. But these methods are very have their own advantages, but they all have to use supercells if you want to calculate or simulate a exciton polaron that is very large. So, and the scaling is not very good for those methods. So we want to develop a method that can be as accurate as those methods, but can be much more efficient in terms of calculating the exciton polarons for a large supercell. So we received this. So we basically get some ideas from the polaron work that was done by Feliciano and his former student Dennis Yu. So basically, this is just a very ultra fast recap of the polaron theory that Feliciano talked yesterday. So basically, in that theory, their starting point is the DFT total energy functional, and basically they will give a trial polaron wave function for psi here, and also the atomic displacement theta tau, and they can express the DFT total energy for this system as a functional of the psi and theta tau. And then they do a minimization of the total energy with respect to the psi and theta tau, and they can get a coupled nonlinear equations. And then they introduce some decomposition, by expressing the wave function in terms of the Cornichon eigenstates. And using that method, they can compute the polarons in a very efficient way, and also is able to capture large polarons. So our theory for the exciton polaron has direct parallels with the charged polarons. So our method is basically we first gave a trial exciton polaron wave function psi RE and RH, because it's a exciton polaron is a two particle quantity. So we have two coordinates, one coordinate for electron, one coordinate for hole, and then the corresponding atomic displacements. And then we have to come up with a way to compute the total energy for the excited state, given the exciton polaron wave function and the atomic displacement. And then we need to minimize the total energy with respect to the wave function and the atomic displacements. And also in the end, we have to introduce some spectral decomposition in order to bypass the supercell. Okay, so as you see earlier, we also follow the idea that we think of this problem as as an excitation problem, meaning that we express the total energy of the excited state as two parts. One is the DFT energy for the ground state, and the other part is the excitation energy. And the ground state energy can be captured by DFT very accurately, and because we know DFT is a ground state theory. And the excitation energy can be accurately captured by the Bethe-Salpeter equation eigenvalues. And here is a very compact form of the Bethe-Salpeter equation. And the eigenstates have two indices. One is the exciton band index. The other one is the exciton momentum. I want to remind you that this exciton momentum is often neglected if you are only interested in the optical property absorptions, because usually the light field carries very small momentum. So that basically means that we also transfer a small momentum to the exciton, and that's why we only consider the Q equal to 0 cases for the optical absorption. But the finite momentum Q is gradually being appreciated in the community. And I will show you that this is also very important in the case of the exciton polaron. Okay, so now we have a way to express our excited state total energy. That is the ground state energy for the equilibrium structure, the non-distorted structure, plus the elastic energy that is induced by the lattice distortion, and the excitation energy for the distorted structure, which is basically the expectation value of the BSE Hamiltonian. And the Hamiltonian corresponds to the distorted structure, which is an unknown quantity in principle. And we do not want to compute this quantity explicitly, because the distortion may happen in a very large supercell. And if you want to evaluate this Hamiltonian in real space, you have to use a very large supercell, which is exactly what we want to avoid. So to avoid the explicit evaluation of this thing, we do a linear expansion. So basically, we expand the BSE Hamiltonian for this distorted structure up to linear order. The first order is the BSE Hamiltonian for the undistorted structure, which you can evaluate from a unit cell. So that's much cheap. And also the first order variation of the BSE Hamiltonian, which you can evaluate from some perturbation theory. And this can also be done within unit cell. So in principle, we can finish this calculation without having to use supercell. And it's already encoded in this theory. And now we have a functional for the excited state total energy. We can do a minimization of the total energy with respect to the wave function psi and the atomic displacements. And if we minimize the total energy with respect to the psi, you will get this equation, which is very simple. You have the first part, that is the BSE Hamiltonian for the undistorted structure, and the first order variation of the BSE Hamiltonian. And if you minimize the total energy with respect to the atomic displacement, that will give you the second equation, which gives you the how to get the displacement from the wave function. And this C here is the interatomic Fox constant matrix. And as I said, we want to explicitly avoid the use of supercell. So we introduce a spectral decomposition, or like a linear combination, to kind of decompose this exciton polaron wave function. We write it as a linear combination of the Bethe-Salpeter equation eigenstates, which is omega SQ, that you can compute from the unit cell, the non-distorted structure. Okay. And this ASQ is what we want. Is what we want to compute in the end in order to get the exciton polaron state. And this is not to be confused with the Tamm-Dunkov approximation when you're trying to solve the Bethe-Salpeter equation. So basically, in the Tamm-Dunkov approximation, you are gonna express the BSE eigenstate omega SQ as a linear combination of the transition pairs that are here. So basically, in the end, we have to combine those two together in order to have an equation in the reciprocal space. Okay, so basically our next task is to put this expression back here and also use this expression here. And we can do some algebra. And after, if you are patient, you can arrive at a set of equations that have this form. Okay, and if you are tired or hungry, so that you are lost in what I just said, this might be the most important slide that you want to focus on. So this is basically the exciton-polaron equations in the reciprocal space. And you can see this is very similar to what you saw yesterday for the polaron equations. The only difference is that now we need to know the BSE eigenvalue instead of the Cohen-Sham eigenvalue. And we need to know the Exciton-Phonon coupling matrix element, which is this G. That depends on the Bethe-Salpeter equation eigenstate and the electron-phonon matrix elements. So basically, we can use this expression to construct a so-called Exciton-Phonon matrix element. And we can put this quantity back here and solve this equation iteratively. And in the end, when the calculation is converged, you can use the converged A coefficient to reconstruct the exciton-polaron wave function in real space. And because now there's nothing that is dependent on the real space coordinate, you no longer need the big supercell to do this calculation. Everything is sampled in a unicell. Okay. Now we have the theory here, and in principle, we can implement the theory with the help of some first principle software such as Quantum Espresso, PerkGW, EPW, and so on. But before doing like a full-blown ab initio calculation without knowing what to expect, we first apply this model to apply this theory to a model system to get some intuition of this theory. So to that end, we use the one-year exciton model to represent the exciton part. So basically in this model, there are only one electron hole pair that is having attractive interaction, and the electrons and the holes are represented by the parabolic bands, respectively, separated by a gap. And in the phonon part, we only take into account a single optical mode with constant frequency, and the electron-phonon interaction is in the form of the Froelich electron-phonon interaction. So it has this divergent behavior as the phonon momentum approaches zero. And because we want to solve this equation variationally, meaning we want to introduce a wave function, a tri-wave function that has some dependence on the parameters, and we can solve the equation by varying the parameters to achieve the lowest energy, to achieve some local minimum. So we need to introduce some ansatz for this problem, and we just introduce the hydrogenic ansatz in the reciprocal space. And if you do a Fourier transform, this will go back to the later, we'll go back to the more familiar hydrogen wave function, 1s hydrogen wave function in the real space, but we're just dealing with them in the reciprocal space. Okay, so that's the model systems that we use for our theory. And if we do some math, we can get some plot like this. We will finally express the formation energy as a function of the variational parameter, which is this Rp. And this formation energy is relative to the free exciton energy. So if it has a positive value, then it means that the free exciton has a lower energy than the exciton polaron, and meaning there's no localized exciton polaron. And if the energy is negative, then you can have some localized exciton polaron, which is what we want. And as you can see, if I choose my whole effective mass, five times of the electron effective mass, then you can see that no matter how I change my variational parameter Rp, there is no localized solution. Everything is positive. But if we artificially increase the difference between the whole effective mass and the electron effective mass, you can see we start to see some local minimum, and it's pretty localized. And I want to remind you that this variational parameter represents how localized the exciton polaron in real space. And another interesting observation is that if you zoom in this part, you will notice a little barrier between this localized solution and this fully delocalized solution. And that basically indicates that if you were to do this, if you were to implement this theory within the first principles, then it is very likely that you will be trapped into some local minimum, or even if you have a very bad initialization for your self-consistency, then it's very likely that you will arrive at this fully delocalized solution without ever touching this, this global minimum. So we have to be smart about the initialization for our self-consistent solution. Okay, so now we have some ideas about this theory. We can move on to the first principles implementation. And this is basically the workflow for the first principles calculations. So you first generate the Cohen-Sham wave functions for and the variations of the self-consistent potentials from the quantum espresso using the pw.x and ph.x. And you can use the EPW to construct the electron-phonon matrix elements in a uniform grid. And the reason why we use EPW is because it can make sure it has very good control of the gauge. And the Zhonglu just said the gauge can be a very big problem if you're not careful about that. And simultaneously, we use the same set of wave functions to construct the BSE Hamiltonian, and then perform the diagonalization to get the Bethe-Salpeter equation eigenstates in order to construct the Exciton-Phonon coupling matrix element, and we want to make sure the gauge consistency. And now we can move back to EPW and combine the Electron-Phonon and the BSE eigenvector to construct the Exciton-Phonon coupling matrix element and solve the Exciton-Phonon equations in the reciprocal space, and then do some post-processing, such as computing the charge density in real space. Okay, and since this feature is not really released yet, so I will only give you, some ideas of what the input files would look like when the feature is public. So basically, it's a 3-step calculation in the EPW big step. The first step is to construct the Exciton-Phonon matrix element, which you just turn on this flag. And you specify how many valence bands, how many conduction bands, and how many exciton bands you want to use when constructing the exciton-polaron equation. And then you build the exciton-polaron equations and solve them iteratively to achieve convergence. And in this case, in this second input file, you just turn on this exciton-polaron flag, and then you specify what your initialization is and how many steps what's the maximum steps that you want to set for the exciton-polaron calculation. And in the third step, you just, with the converged results, you move on to plot the electron density and hole density associated with the exciton-polaron. But again, this feature is not released yet, and we are working very hard to try to make it public in the next release or the next release. But you can see the structure is very simple, and I believe everyone can perform this calculation very, very easily when it's released. Okay, so now with the workflow established, I can show you some examples of the calculations. The first one is the lithium fluoride, which the reason why we chose this material as the first example is because the difference between the hole effective mass and the electron effective mass is very large. So that basically indicates it's much easier to find the localized exciton-polaron from this system according to the model I just showed you. And second, because this is a very small system, there are only 2 atoms in the system, so we can try to converge our calculations with respect to a lot of parameters. So that can give us some ideas like what the convergence behavior is for this type of calculations. And here is the result of I'm showing you here is the charge densities for the exciton-polaron wave functions. And as I told you, these are 2 particle quantities. So there are actually 2 charge densities. One is the hole density in the exciton-polaron, and the other one is the electron density in the exciton-polaron. And you can see they are all very localized. Perhaps the hole is more localized than the electron. And to have more ideas of these 2 objects, we can compare them to the charged polarons, like independent charged polarons, respectively. So here is the independent hole polaron, and here is the independent electron polaron. And you can see that the hole density of the exciton polaron is very similar to the hole polaron. Whereas for the electron polaron, it is much more delocalized than the electron density of the exciton polaron. So what does this mean? Well, we can think, from the comparison, we can think of the process of forming the exciton polaron as two steps. The first step is the independent formation of the hole polaron and electron polaron. And the second step is that when you put those two objects together, they will form a new particle by the Coulomb interaction among those two between those two objects. And because the hole polaron is more localized, it's more stable, it can sort of anchor the whole object, and it will attract the electron density to make it more localized. And conversely, the delocalized feature of the electron polaron can kind of pull the whole polaron apart to make it slightly more delocalized. And this slightly more delocalization can be seen here in those parts. If you focus on those corners, you will see that there is some charge density around here that is absent or very small in the whole polaron. And of course, we can, by the way, you will be able to reproduce these charged polarons this afternoon in the tutorial session led by Professor John Lafuente-Bartolome. And also you can compute the the atomic displacements for the excitonic polarons that take this shape. And you will also find this afternoon that this displacement pattern is very similar to the whole polaron, actually. And moreover, we can have we can analyze which phonon modes has more contributions to the formation of the exciton polaron. And here is the decomposition of the phonon contributions. And basically the yellow discs represents how large the contribution is from each phonon mode to the exciton polaron. And you can see that, well, some optical modes have very large contribution to the exciton polaron, which makes sense. But what might be surprising is that some acoustic modes also has very significant contribution to the exciton polaron. So basically, that signifies why we have to use the ab initio calculation in the end to compute the exciton polaron, because these acoustic modes are often neglected in model calculations. Okay, we also perform another test on a different system. This is called a vacancy ordered double perovskites. Even though it's a perfect crystal, but because of all the octahedra are not connected to each other, so people call this a vacancy ordered double perovskite, but it's a perfect crystal. And in this case, we also found a solution where there are very localized exciton polaron. And here is the hole density of the exciton polaron, and this is the electron density of the exciton polaron. And they have very similar localization length. And also, of course, we can figure out the atomic displacement as well as the phonon contributions. And in this system, we just found that this optical modes has the most contribution to the formation of the exciton polaron. Okay, this is the last slide of my presentation. So I hope I convince you that we have already developed an ab initio theory for exciton polarons that does not need supercells. And this theory can be implemented very straightforwardly using EPW and the Berkeley GW. And the advantage of this theory is that first, it doesn't need supercell, and second, it can yield the formation energy, the charge densities, the lattice distortions, and the phonon contributions all at once. And here are a few references if you are really interested in this topic, and they have all the theories, derivations, and all the pretty figures in those papers. And yeah, with that, I'd like to thank you for your attention.
Very nice talk, Dr. Dai. So we have time for some questions. go back to slide number 11?
Sure.
How do you make the initial guess to make sure that you don't cross the barrier from where you see the localized polaron to where you see both the localized and delocalized?
Yeah. Well, very good question. So actually, when we were first implementing this theory, we found a lot of problems finding the best initialization. So the way that we did that is that we basically artificially increased the exciton-phonon coupling matrix elements. And by artificially increasing that, okay, sorry. So by artificially increasing the exciton-phonon coupling matrix element, and by doing that, we can bias the equation to find the localized solution. And with the solution from this artificial calculation, we can use this solution as an initialization for a second run, where in the second run, we recover the regular exciton-phonon matrix elements. And that way we can, for the most cases, we are able to find the localized solution. In principle, yes. In practice, we haven't done that yet because the interpolation of the exciton bands is just recently being worked out by a group. And it's not really, this feature is not really public yet. So we don't have any available software that can allow us to compute, to interpolate the exciton bands. But if that is public someday, then we can basically combine that feature with the interpolation of the phonon band structure and to interpolate the exciton-phonon matrix elements. Thank you.
I just one comment. I was wondering whether you would try to do this on silicon dioxide case that we look at. The reason I ask is because that the Excitron-Phonon there actually involves breaking in bond, silicon oxygen bond. So the whole system structure changed tremendously. So that means that it involves all the phonons in the whole Brilliant zone. Yep. It'd be nice to try your method on that.
That's a very good question. I try to hide this part, but yes, we did some tests on this silicon dioxide, and we just encountered some convergence problem, meaning that we have to use a lot of exciton bands to convert the calculation, and it's still not yet converged. So still working on that. But yes, I think a general feature of this theory is that it's designed to deal with large exciton polaron, meaning the distortion is relatively weak. If you are dealing with a very localized exciton polaron with very large distortion, then it's possible that our predictive theory is not very able to capture that feature. And in those cases, you have to do explicit real space relaxation. And yeah.
So